For today's lab, we're doing something obviously different. It's mostly lecture, but you'll be working out some problems and doing a little mini lab. And you'll need to turn in this thing here completely filled out. So take one down, pass it around. So as we go through, you'll either be working out the problems amongst yourselves, or I'll be working them out and you'll be following along. So just make sure you stay with us. The first thing is just a review. We're pretty much, at the end of today, we're going to be done with our mechanics portion of the class. That is, we're done with talking about things moving and why they move and how they move. And we're going to move into thermodynamics and then into waves. And, yeah. You want more? Then there's probably one extra over here. Is there one extra? No. Okay, did somebody take two?
I can give up mine.
Okay. I traded 15, so there'd be one for you. Is that an extra one?
Yeah.
Okay.
Nice.
I traded an extra one for you. Okay, so first, quick review. When you are looking at a problem, the first thing you do, remember, you get points for this on those synthesis problems, and it's not because it's something fun to make you do, it's because it's how you think about solving the problem. So the first you identify is what type of problem it is. And if you identify that it's a kinematics problem, then you have things like kinematic variables you need to worry about and what the kinematic equations are. Obviously, you're going to be given the kinematic equations on a test, but you still need to be able to differentiate them. And I'll be going through the next slide after I finish this one is the actual steps for the different ones. Then we had Newtonian dynamics. Kinematics is how things move. Dynamics is why they move. So Newtonian dynamics is Newton's laws used to explain why things move. And so we have Newton's 3 laws of motion, got to understand what forces are. And rotational motion came in that area because we had to understand centripetal acceleration as an acceleration that we use in the Newtonian dynamics. Then we had work-energy dynamics, where we're using the work-energy relation instead of Newton's laws to do equivalent solutions. So in that case, you better understand what work is and what kinetic and potential energies are. I didn't think it responded in the first book, so I clicked it twice. And that work-energy relation. Then we had equilibrium problems. That's what we have just finished. Equilibrium problems are problems where you have either stationary, what we call static equilibrium, or dynamic, where it's moving equilibrium. The conditions for equilibrium, obviously you need to be able to identify those. Some of the torque is 0 and some of the forces is 0, which means no acceleration, so constant velocity. No angular acceleration, so constant rotational velocity. Right, so 0 velocity is a constant velocity, but so is 60 meters per second east, which would be super fast if you're doing it in a car. Right, so make sure you understand what the conditions are of equilibrium. Simple machines is an example of equilibrium, so we're going to be starting off with simple machines, and then we're going to do rotational dynamics at the end of the day. So now I have specifics, and if you look on your sheet, this is what you have on the front page, of how to address each one of these types of problems. So kinematics, which is studying how things move. First, draw a diagram. So if you identify this is a kinematics problem, it's just motion without any reasons why. Then draw a diagram with appropriate details, you know, the starting condition, the ending condition, whatnot. And if it's two-dimensional, make sure you identify what directions the x and y. Identify your known and unknown kinematic variables, position, speed, acceleration, and time. Identify the relevant kinematic equations. How do we usually identify which equations are relevant? Yeah, basically in terms of your variables. What variables do you have and which ones are you looking for is usually what you do. And then solve your equations. These last two steps are always the same. Solve your equations and check that your answer makes sense. So if you identify that it's a kinematics problem, then you have your steps already set up. Next, Newtonian dynamics, ones that are going to be solved using Newton's second law. If you identify, oh, this is something that is having motion because of forces, then you're going to say, I'm going to need to follow this set of steps. So you draw a diagram with appropriate details and dimensions. Then you identify the object that you're going to apply Newton's second law to. That object could be the ball. The object could be the spacecraft with everything in it. It could be, two things. You have to identify what the important thing is that you're going to be analyzing. Once you've identified, then you draw a free body diagram for your object and apply Newton's second law. You do it to apply Newton's second law. Break the forces into components, once again, for applying Newton's second law. And then you apply Newton's second law. And after you've applied Newton's second law in each component direction, same last two steps. Solve and check if the answer makes sense. Right? It's a very straightforward process. Once you've identified the type of problem, there'll be lots of different variations of problems, but it's still the same method for solution. Then we had work-energy dynamics problems. So some problems you could solve either with work energy or with Newton's second law. For instance, should I go fast enough? The last problem I have scheduled for today, you could solve it either with work energy or with Newton's second law. In most cases, which way is going to be simpler? Work energy, because you don't have vectors to worry about. You just care about the starting and ending conditions, and then if there's any non-conservative work done. So work energy, draw a diagram with your kinetic and potential energy at each important point. Usually that's the start and end, but sometimes you have a midpoint that's also important. So make sure you identify those at each location. Identify any non-conservative forces. So obviously you need to know the difference between conservative and non-conservative. One of the questions we had on the test was about the types of forces associated with potential energy. Conservative forces are the ones that have potential energy to identify. Non-conservative, no potential energy. Conservative forces, ones that are going to give back energy, that's why we have potential energy for them. And examples are gravitational force, spring force, and then others that we haven't dealt with yet. Apply the work-energy relation between the important points. Remember the work-energy relation? I am told that I'm finally going to be able to have PowerPoint working correctly soon. Work net is equal to change in kinetic energy is one way of writing the work-energy relation. Using the definition that work net is work non-conservative plus work conservative. It's like my brother and I do a job, work Richard and work Ron, add them up and you get the total work. You have the work conservative, the work non-conservative, add them up, you get the total. You can also make that into work non-conservative is equal to change in kinetic energy plus change in potential energy. And that's the form we usually use in these problems. The work non-conservative is change in kinetic plus change in potential. And then solve the equations and check to make sure your answers make sense. Next type, equilibrium. Equilibrium, what we've just been working on. Draw a diagram with appropriate details and dimensions of two-dimensional. It's kind of getting old, huh? Draw a diagram every time. Identify the rigid object you're working with. Draw a force diagram showing all forces where they act. This isn't the technical free body diagram where you show all the forces acting at one point. You're showing them where they act on the object because you have to worry about torques, and torques, it depends on where they act. Then, usually, you start with sum of the torques is 0. The reason for that is by judicious choice of where you sum the torques, you can make at least one unknown force disappear from your equation because the perpendicular distance is 0. Remember, torque R cross F. It's the radius perpendicular to the force multiplied by the force. So obviously, there's underlying things, you have to understand what torques are, what Newton's second law, all those things. So apply the sum of the torques about judiciously chosen location or locations. If necessary, apply sum of the forces equals 0. Sometimes it won't be necessary, sometimes it will. And then solve the equations and blast the ball, make sure it makes sense. And then rotational dynamics. That's what we're doing today. Now, rotational dynamics can be done two ways, just like we could do other dynamics. You can do it with force and torque, or you can do it with work energy. So I have here just the forces and torques method. The work energy the description of how to do it comes out exactly the same as the work energy did before, so I didn't write a separate description for it. But if you're doing forces and torques, well, of course, draw the same diagram, basically. Identify your rigid object. Draw a force diagram showing all the forces where they act on the object. Apply, this is a new equation. Sum of the torques is equal to I alpha. So we just got to what this I is, the moment of inertia, last class period, right? We only had lecture for like 15 minutes. That's basically where we got to. Sum of the torques, remember Newton's second law, sum of the forces is equal to mass times acceleration. The rotational equivalent to a force is a torque. The rotational equivalent to a mass is the moment of inertia. And the rotational equivalent for acceleration is angular acceleration. So if you think about it conceptually, that is exactly Newton's second law. Now, as I was telling my students this morning, if you guys like go to the tutorial videos I've created for you on YouTube, there's some guy who is cracking on me because I write this as a vector equation. He's like, it's not a vector equation. And technically he's right, because moment of inertia is more complicated. The moment of inertia depends on the axis of rotation. And it actually is a tensor. It's a 3x3 matrix of values. But for our purposes, we're always going to use the moment of inertia is this in the x direction, this in the y direction, this is in the z direction. So it works out for us, as long as we remember, that putting it as a vector equation, you have sum of the torques in the x direction is I about the x-axis times alpha in the x direction, and it goes like that. Apply sum of the force equals mass times acceleration in each component direction, and then find the relationship between acceleration and angular acceleration. You have to have something to tie together the rotational and the linear, or translational as we like to call it, variables, and then solve and make sure the answer makes sense. Now these we haven't done yet. So I'm going through the steps here, and right now it should be fuzzy in your head unless you're really ahead of the game. You're ahead of the game? Excellent. So let's get started in with the problem. Now this one I'm going to lead you through, but I'm going to ask lots of questions, and you have steps that you have to fill out on that form. So actually, Andrew, since I kind of forgot what the steps are they have to fill out, I want to make sure I actually answer. All right, so we have this problem. An 84.3 kilogram window washer creates a hanging scaffold using a uniform. What does uniform mean? Okay, it's the same everywhere. So that means that, as Randy said, the density is the same everywhere. It's going to have its center of mass at its geometric center. So it's 3 meters long. Its center of mass is at the midway point, 1.5 meters from the edge. Why is that important? Because we can treat the force of gravity as if it acts at the center of mass. In fact, sometimes people talk about the center of gravity. Center of gravity and center of mass have different technical definitions. But if you're on the surface of, if you have a uniform object and the acceleration of gravity isn't changing, they're going to be exactly the same. And even if it's not uniform, if the acceleration of gravity isn't changing, it's still exactly the same. So that uniform word is an important thing for understanding the problem.
I have a question.
Yeah.
What is a scaffold?
A scaffold is something that you stand on as a platform to do your work.
What?
Something you stand on as a platform to do your work. So he's washing windows. He needs a platform to stand on, so he washes the windows on the 275th floor of some imaginary building.
Okay, it looks like yeah, you know when buildings are under construction and there's like stuff next to them? It's like for the workers to stand on while they work.
But this one here doesn't have your X cross pieces. It just has 2 ropes holding it, one on each side, as described later. So it gives us the mass of the window washer, the mass of the board, the length of the board. It tells us where the window washer is standing, and it says what are the tensions in each of the ropes. How do we solve these problems? We just went through the steps. Which type of problem is this? Okay, it's an equilibrium problem, which has Newton's second law involved, but it's a specific version where the acceleration is 0 in Newton's second law. And we use the rotational equivalent as well. So the first thing is, the concept here is equilibrium. And so if it's an equilibrium, you automatically have two conditions of equilibrium. What are those two conditions for equilibrium? Okay, somehow my ears heard some of the velocities is 0. Of course, that's not what she said.
Even some of the forces.
Some of the forces, that sounds better. Some of the force vectors equals 0. And then I know I heard somebody say some of the torque vectors equals 0. So we have those two conditions because we identify it's an equilibrium problem. So we know how we're going to go through this already by identifying its equilibrium. So now we have to draw a diagram. Now here's where I'm a genius. Remember, this here won't even save because the problems we're having. So I have to change over to using a different app to actually solve the problem. And it's going to be like 7 pages down or something. Come on. Okay, so I'm going to rewrite here because the other stuff won't. Concept is equilibrium, which gave us our two conditions. Some of the force vectors equals 0, and some of the torque vectors equals 0. So then we draw our diagram. And so, like Oksana was asking, what is a scaffolding? We have, here's the board that measures 3.00 meters in length. And then we have a rope holding it up on each side. And then finally, we have a man standing on it. Or a woman. I don't think I just specified gender. And that person is standing, was it 0.75?
Yes.
0.750. I got 3 significant digits on there. Okay, so there's a diagram. What's missing from my diagram?
Forces.
The forces. And where do I draw the forces? On the diagram, yes, but more specifically, where they act. So start naming off forces. Okay, I heard tension, I heard gravity. Let's go one at a time. Force tension. Where do I have a force of tension? On one of the ropes. And where's the other one? The other one, yes. So I'm going to have here force of tension 1, here force of tension 2. How do I know they're going up?
That's a great question.
They're going whatever. Yeah, somebody said because tension. Tension force always goes in the direction that the cable is leaving the object. And so since that rope is going up, the tension has to be going up. So I didn't have to say, well, because I'm not a dope, I know that it would fall without the rope, so they have to be holding it up. I mean, that would also be true, but saying because of the way tension works is a smarter answer. Right? I mean, smarter answer, whatever. It's a more technically good answer. Okay, so then, go ahead.
We're trying to find out, like, if we have to figure this out, why is it equilibrium,
Okay, why is it equilibrium? I asked what type of questions people said equilibrium, I just moved on, but why is it equilibrium? Because everything is at constant velocity of 0. It doesn't have to be 0, that's why I said constant velocity. But in almost all of our cases, it is 0. It also has to have constant rotation. Once again, 0. If it's rotating, he's kind of in trouble. So that's the method for identifying that it's equilibrium. Okay, then somebody said gravity. We have gravity for 2 things. What are the 2 things we have gravity for? Okay, we have the force of gravity for the man and the force of gravity for the scaffold. Where's that force of gravity? Or I'll put for the, scaffold. Where's that force of gravity for the scaffold act? At the center, because that's where the center mass is.
Right.
You know the guy standing on it?
That's the gravity of the scaffold. We have the force gravity on the man separately. I suppose we could, but it would make life harder.
And then you've got normal force on the man.
Ah, what was our object?
The board.
The board. There is a force normal acting on the man, but that's not acting on the board.
Right, so we don't care.
So we don't
Force
care.
of the man, I think, on the ball?
Yes, the force of the man is pushing down the board.
That's the gravity.
That's if you want to be technical, yes. The force of gravity is acting on the man, and the man is then acting on the board separately. That is a technically correct description. Randy.
Because it's suspended in the air, there's no force moving.
Well, this scaffolding is suspended in air. So there's no force normal. If we were looking at the man, there would be a force normal because he's standing on the scaffolding.
So these are all forces.
Then this is they. So what's our next step? These days we have to make sure we pronounce that word carefully. Sound like you said torque, and that's not going to happen. So our instructions say choose an appropriate location to sum the torques so that one of the forces will be eliminated. Now, which forces do we know and which do we not know? We know the two gravity. We don't know the two tensions. So where should I sum the torques to make one of the tensions make no torque? At one of the two ends, because if you sum the torques about a point that is on the line of action of a force, that means the force points right to it. Even if it's not where it acts, the force points right to it, then the perpendicular distance is 0, and you have no torque. Their torque is R cross F, which has a magnitude of the perpendicular distance from the pivot point to where the force is acting. So they said to choose one of the ends. I'm going to choose the left end because, hey, I'm happier with the left end than the right end. I'll call this left. I'll call this right. And so I'm going to do some of the torques about the left end. So the equation for torque, remember, here's the full equation. It's R cross F. So the magnitude of the torque is equal to R perpendicular times F, or RF times sine of the angle between the vector that points from the place I'm summing the torques to where the force acts and the force itself. So if I do the sum of my torques, I'm just going to take each force, and as I've told a number of students, normally if I'm solving a problem, like if you're doing it on a test, there's no point in putting in a term that has 0 torque, right? You can do that one in your head without thought. But I put them in when I'm showing you guys just to make it clear that I didn't forget a force. So for each force, I'm going to put its R perpendicular times the force. Notice I always try to put the radius first and then the force to make sure we don't start thinking that it's force times distance. So for the first force, that's force tension 1 at what's the perpendicular distance from L to where force tension 1 acts? 0. So I'm going to put 0 for that distance times force tension 1. Now my next one is going to be, I'm just going in order. So the next force, just going in order from left to right, is the force from the man.
Right.
Is that going to make a positive or a negative torque?
Positive.
Yeah. I was wondering how it was wrong. No. We call it the right-hand rule.
It does the same.
I was looking at your fingers. I said, your fingers are absolutely right, but your thumb's wrong.
There we go. So yes, okay, I got it.
So it's the right-hand rule. Index finger points in the direction of the radius. So I'm going from L to where the man is standing. So that means my index finger needs to point that way. And then keeping my index finger pointing that way, I want to rotate my hand so my finger points the direction of force, which is down. And then my thumb points the direction of the result. My thumb points into the screen, hence that's what we call negative. Or remember what Oksana said. If that force would make it have a clockwise rotation, it's a negative torque. If that force would make it have a counterclockwise, or some people say anti-clockwise, rotation, then it's a positive. So this is negative. You can get there either by the right-hand rule or by what direction that force would make it rotate if it was the only force.
So clockwise is what way?
Clockwise is negative. Counterclockwise is positive. Excuse me?
Any situation?
Yep. That's how we define all directions. That's why you have right-hand threads on your screws. Right-hand thread means if you rotate it clockwise, it's going to go away from you. If you want to take it counterclockwise, it's going to come out toward you. Okay, so we have minus that distance for the man was 0.750, and his force was the mass of the man times G. And then we go to the next force, force of gravity from the scaffolding. Is that a positive or negative torque? Negative. It's exactly the same orientation as the preceding one, so it had to be the same sign.
And it's negative 1.5 meters.
Distance is 1.50 meters.
Why is it MMG?
Mass of the man. Or mass of the painter. Since I don't think I was gender specific here, was I? Yeah. This is mass of the scaffolding times G. And then I have my final one from tension 2. Is that a positive or negative torque? It better be positive or else my whole thing is going to be swinging in a counterclockwise direction. So the last one's going to be positive. You get there by using, again, the right-hand rule. R points that direction, orients my fingers so they can point up, keeping my index finger the same and the thumb points out. Or you can just say it would make it rotate in a counterclockwise direction, which is positive. Question?
I had, no, we're
So what's the perpendicular distance from L to R? 3. And what's the sum of the torques equal to? So now we just need to solve this bad boy for force tension 2. So let's just move these terms to the other side of the equal sign, which means we add them. And I'm going to have 3.00 meters times force tension 2 is equal to 0.750 meters mass of the man G plus 1.50 meters mass of the scaffolding G. Divide everything by 3 meters. Notice my units of distance, as long as they're the same, they cancel out, so I'm fine. And I'm left with the force of tension 2 is equal to 0.750 meters over 3.00 meters times the mass of the man times G plus 1.50 meters of 3.00 meters mass of scaffolding times G. Well, obviously, 1.5 over 3 is 1/2. 0.75 over 3, that's a little bit tougher.
1/4.
I think it is, but I got to actually think. You did on your calculator? So what's the mass of the man? It's 84.3, not 48. Times 9.80 meters per second squared times 3 quarters plus 1/4. Yes, not 3/4. My brain. We all need them. Mass of scaffolding is 8.25 kilograms.
Why did you put 31 grams?
84.3 kilograms. That's a K. Sorry, that's handwriting. I used to have to miss recess to practice my handwriting in grade school. Didn't take. So what do we get for that force of tension 2? Okay, and I am blindly trusting 246.9, is that what you said? So 247 to round off. Okay, so there's force tension 2. Now, what do you think force tension 1 is going to be compared to force tension 2?
Going to be bigger.
Yeah, I've got some the same, some bigger. Yeah. Yeah, we found 2. So we know the value for 2. Is 1 going to be bigger or smaller is the question? Or the same? It's going to be bigger because he's standing closer to that one. Okay, so that's just a general term. I don't have the value for it. Now we need to get its value. So that's where we get to the last one. Use either of the 2 equilibrium conditions to find what force tension 1 is. Which one would you prefer to use, Oksana?
Well, we go back to the question because I don't know how you thought the notes was on the left side.
Because the picture, the picture which came from the words, it didn't actually matter which one you chose. It just says that he's standing 0.75 meters from one end. I just chose it to be the left end. Right? This problem is agnostic of left versus right. Just like I should be in political terms, at least in front of the classroom. So which condition of equilibrium would you prefer to use to find the force from the other one? Say it out loud. Yeah, I would go with what Sarah says. Why the sum of the forces? There's no multiplication involved there. It's just addition. So I will do for the last one, I'll just write it right here. Sum of the forces in, let's define x and y directions. Now I haven't used the directions yet, but here I will. In the y direction equals 0. And when I look at my picture, what do I have pointing in the plus y direction? The 2 forces of tension. And what do I have pointing in the negative y direction? The 2 forces of gravity. So I'm looking for force tension 1, so I just move everything else to the other side of the equal sign. Force tension 1 is equal to force gravity man plus force of gravity scaffold minus force tension 2. So that's going to be G times the sum of the masses. Minus my 247. I should have put 9.8, I suppose. And so once again, you just put that in the old calculator. And 84.3 plus 8.25 is 92.55 times 9.8. Somewhere in the ballpark of 900-ish. 900 minus 247 is way bigger than 247. So there we've worked out an equilibrium problem. Now, why did I work out the equilibrium problem? Well, you need to see it modeled. And importantly, questions like the one Judith asked, how do we know it's an equilibrium problem? If you can't answer that question, you're going to have a real tough time doing the rest of it. But if you can answer that, here I gave you specific steps to follow. On the test, you're not given those. Those are the things that you have to know from what I summarized on the first sheet. Any questions about this problem?
Can we just go back to the first equation where we found the forces to, was it?
The sum of the torques?
Yeah, so
Yes. What about it?
just like going back to
Just checking to make sure you. When I was in graduate school, our teacher accused us of being mindless scribes, writing down whatever he wrote without thinking it through. For the most part, he was right. Yeah.
when you're doing the force of someone force of tension L, what is CO?
Okay, this is torque. This is the Greek letter tau. That's why it's got the front thing on top. What is what? Oh, that's not a C. That's a parenthesis.
Ah,
I wanted to make sure that I specifically put in each force even though this one causes zero torque because the perpendicular distance is zero. So this is the perpendicular distance times the force. Right?
Okay.
Because at this point, the perpendicular distance between this point and where this force acts is zero. And so that's 0 times force tension 1.
And then you just add it all together.
Yes. So the next one came at 0.750. So 0.750 times it minus sign because of direction.
Okay.
Next one was at 1.5 meters minus sign because of direction. Next one at 3 meters plus sign because of direction. Okay. Now one that's a.
Wait, hold on.
Yep.
Where did our 1.5 come from?
Okay, because the force. Come on. I don't even have the stylus close. You should be moving. Because the force of gravity on the scaffolding was acting at the center because it said it was a uniform beam.
Okay, so just half of it.
Yeah, so that's half of 3. Right.
Okay, and before we move on, like we were doing the second half, like finding tension, force tension, 1.
Okay. Yes.
So how come we're multiplying the 9.8 times the rest?
I did it in my head. I probably shouldn't have. I've already taken 40 minutes, and I expected to do this in less time.
Okay.
So those two terms I put in the black parenthesis, it's mass of the man times G plus mass of the scaffolding times G. And so I just factored out the G.
Okay.
Okay, this next part is all you, with a little help from our friend Andrew and me. So now you're going to actually do an experiment. Now for this experiment, you're going to do it both experimental method and theoretical method. So you're going to have a meter stick and a hanger, a fulcrum, 2 hangers that have a little wire thing hanging from them, and one that doesn't. First thing you do is you put the one that doesn't on your meter stick, slide it to the center, and different ones have different ways of measuring position. This one here, you just look at the edge right here to determine its position. Right now, I'm putting this directly on the center. It's probably not the center of mass. We need to locate where the center of mass is. Also, this one here is useless. This one's stripped. So let's go for one that hopefully is not stripped. I'm sitting there turning, it's not getting tight. I'm like, how far do I have to turn? Okay, so I put it on the center. I'm going to see if it balances. Going with no. I need to shift this toward that direction a little. We'll see if it balances. And you just moved it too far. So you experimentally find where you need to put it to make it balance. Now, one thing to note, so I'm still not there. Getting close though. One thing to note is that I have these little knife edges are on the top half of my meter stick. If I put it upside down like this, it's unstable. If it's balanced, it'll stay balanced, but if it's not balanced, it will just keep going. This one here, this direction has a little bit of correction because the center of mass is below this. And so if it tilts this way, the center of mass went up. So that tries to bring it back down. So you have a little bit of leeway instead of having to have it exactly right. So that's still not perfect, but it's pretty close. So you want to try to get it as close to perfect as you can. I'm a little bit sensitive. But I'm going to stop here unless it's worse. Yeah, I'm going to stop there because I don't want to take all the time trying to balance this one. Then you need to use the triple beam balance to measure the mass of each one of these. So make sure you know which one's which. These both have 1 marked on them. This one here has a 2 above the 1. This one only has a 1. So I can tell the difference. I'll call the one that has a 1, 1, one has a 2, 2. I'll measure the masses of each. Then you take the one that you called 1, and now you're going to put it so that the knife edges are down. So the opposite orientation. In other words, the screw is going to be up on these, but the screw is down on that one. And put this one on so it goes to the 25 centimeter mark. This one here, you measure its position differently. It has a little pointer right here. That's where how you measure its position. Those are the only two types we have. So I'm going to put this so the pointer's at 25 centimeters. We're right on the button. And then I'm going to hang a 50-gram mass from it. 50, I think this is 100. My 50 is missing as luck would have it. Okay, so I'm going to put a 20 because my 50 is missing. Andrew, can you grab the mass sets? They're just sitting on the cart back there. So I'm putting that there. I'm going to hang this from my other hanger and find the position for it to balance. So bring this in here and find where I have to put it to make it balanced. And so it's kind of a trial and error thing. And once you find it, getting close. Once you find it, okay, it's as close as my balance was. Well, just set it down there, just because the students will need them. Then you're recording the positions. Well, this one here, what's its position? 25 centimeters. This one here, you record its position because it's not going to be exactly 50. This one here, you record its position. Then you're also doing the work theoretically to calculate what those are for equilibrium conditions. So it's an equilibrium problem. How do I know? Because it's supposed to stay balanced with no angular acceleration. And so I apply my equilibrium conditions to find the balance. So we have 5 groups. So 1, 2, 3. Perfect. Each table's a group. So get your stuff. Well, we're doing this problem, and then that's that one. So we're going straightforward.
Was this the bad one? I have no idea. I think one of those two is to measure. One of the 2 of them is have hangers, and then one of them is to measure. I don't care. So it's probably not noisy. That's all.